Hi, Jason. Maybe we can begin. So, some people will join late and some are on YouTube. Okay, welcome everybody to this week's Marana Raichudhuri seminar series. Today, our first speaker is Jason Cristiano from Kyoto, and he's going to talk about cosmic inflation from small scales to large scales. Maybe I'll send you a reminder when 5 minutes are left.
Okay, thank you. Yeah, so it's my great pleasure to talk here in this seminar series. So I am Jason Cristiano. Uh, yeah, now I'm a postdoc at Yukawa Institute in Kyoto University. This is my work based on my work with Junichi Yokoyama at Kafli IPMU. Mainly my work when I was a PhD, when I was PhD student. Yeah, this is some reference. So yeah, I start my talk. So here is the brief content, brief list of my talk. So first, I will give introduction of uh, violation of slow roll approximation, and then I will give introduction about I will give a review on linear perturbation theory, especially the 2-point function, and then after that I will go to the nonlinear perturbation theory. So this is mainly the new result in the part 3 of my talk. uh, Nonlinear perturbation theory means computation of higher point function like 3-point function and 4-point functions at tree level. And also it means that this nonlinearity also induce uh, one loop correction to the 2-point function or the power spectrum. And yeah, later I will discuss some issue on smooth and sharp transition of this slow roll violation of this slow roll approximation. And then after that, I will also explain about this renormalization. So here in the part 3, in the one loop correction, yeah, I will explain the computation of Bayer one loop correction. And then in this part, I will explain on recent progress on this renormalization. And then at the end, I will conclude my talk. So yeah, hopefully I can finish this on time. Okay, so I start from the textbook model of cosmic inflation that is called canonical inflation. So this is the most minimal model of inflation. Uh, so there is inflaton slow rolling down this potential until the inflation end here, and then the action is given by this. So simply Einstein gravity and canonical kinetic term and the potential which realize a slow roll approximation. And then the background is given by this homogeneous and isotropic metric of the expanding universe. So here A is scale factor, T is physical time, and here tau is conformal time. So yeah, this is writing in conformal coordinate. Uh, then we have two equation of motion. The first one is Friedmann equation, simply from the Einstein equation. We have two here. And then second, we have Klein-Gordon equation from the scalar field sector. Yeah, so yeah, I'm sure you are already familiar with this. And then slow roll approximation means we perform this approximation. So the acceleration of this field, phi double dot, is much smaller compared to phi dot. This is the magnitude is much smaller compared to this velocity. Uh, Mathematically it's given by this. And then second approximation is uh, phi dot, the velocity, is much smaller compared to Hubble scale, Hubble parameter. And then it's, the slow roll parameter is defined by this rate of change of Hubble parameter. And then this equality is simply based on Friedmann equation. So slow roll approximation means that we impose these two approximation. And then if we perform this slow roll approximation, the equation of motion becomes given by this. So H square, the Hubble parameter is almost a constant given by phi over this 3 Planck scale. square. And then this phi dot, the velocity of the field, is proportional to the tilt of the potential. So yeah, with this, we can write the slow roll parameter as function of the tilt of the potential compared to the value of potential itself. Uh, so with slow roll approximation, the scale factor can be uh, approximated with this expansion or simply quasi de Sitter. Yeah, in conformal time, it's written by this minus 1 over h tau. With domain of conformal time is negative time domain. Okay. Sorry, can you hear me?
Yes, yes.
Uh, sorry. Uh, yeah, test. Okay, so more on slow roll inflation. So more systematically, we can define the nth slow roll parameter. So in the previous slide, I present definition of this epsilon 1 is defined by rate of change of Hubble parameter over h squared. And then we can define nth slow roll parameter as rate of change of uh, the previous epsilon. So for example, like epsilon 2 is rate of change of epsilon 1 and so on. And epsilon 3 is rate of change of epsilon 2. Yeah, if we substitute equation of motions, or we can write epsilon 1 like this, proportional to the velocity square of the scalar field. And then epsilon 2 can be written like as this. So 2 times epsilon 1 plus the acceleration compared to the velocity. And yeah, slow roll approximation means that we impose all the slow roll parameters and all the n slow roll parameter to have magnitude much less than 1, to have magnitude, to have small magnitude. So slow roll approximation always imply quasi de Sitter because quasi de Sitter is simply epsilon 1 much smaller than 1. So yeah, it's part of this slow roll approximation. However, converse statement is not true. So if we have quasi de Sitter space, then it does not necessarily slow roll approximation is satisfied because we can violate the epsilon 2 and epsilon 3. I mean, we can have large magnitude of epsilon 2 and epsilon 3 and so on, the higher end slow roll parameter, higher than 1. Yeah. So why I'm talking about this slow roll parameter? So okay. Uh, so this is just introduction. I will explain this much detail later. So if we look at the spectrum of power spectrum of curvature perturbation in at the end of inflation at the reheating surface, uh, yeah, the standard slow roll inflation give almost scale invariant spectrum like the brown line with the tilt proportional to the slow roll parameter. And then, yeah, so the power spectrum can be written like this, h square over epsilon. Yeah, so in slow roll inflation, h and epsilon yeah, Hubble parameter and slow roll parameter are almost constant, but still they have small time dependence. So here, the time dependence is evaluated at the horizon crossing of this mode of interest, mode with a wave number k. Yeah, this evaluation give a small scale dependent on this on this power spectrum. So weak k dependence. Yeah, so if we assume slow roll inflation from the beginning until the end, we will obtain this brown curve. Okay, and then yeah, and then it can explain the observed power spectrum I mean, it can explain this CMB spectrum observed in the CMB. So the correlation of fluctuation in this CMB. However, CMB only constrain this power spectrum only within a specific range of this K, only on large scale, where the wavelength of the fluctuation is uh, sorry, where this K is smaller than 1 megaparsec inverse, roughly speaking. And then, yeah, beyond this range, beyond this range, observational constraints are weak enough. So in principle, we can have a theory where the spectrum is enhanced on small scale. Let's say enhanced until this delta S square PBH. Yeah, why I say this delta S square PBH, so I will explain later. Let's say it enhanced, uh, yeah, it enhanced at small scale. Then, how to achieve that? So what kind of theory that can have this kind of spectrum? So from this expression, yeah, we can naively say that, okay, just decrease epsilon 1 at late time. So when it's evaluated at small scale, this tau is equal to -1 over k, but larger k, then uh, this delta S square at that small scale become very large if we decrease epsilon 1. And then, yeah, to achieve this, so we need to violate slow roll approximation. So we can have a large negative epsilon 2 that that rapidly decrease this epsilon 1. So yeah, this is the current observational constraint on power spectrum on the primordial fluctuation. So it tightly constrained on large scale. However, its constraints are very loose on small scale. So we have current constraint from this virus, from this mu distortion, yeah, and uh, from this PTA, and this 10 to the power of -2 is yeah, often labeled as PBHDM. So this is like, so if the fluctuation is large enough on small scale, then it can collapse to significant abundance of PBH, of primordial black hole, after such fluctuation re-enter the horizon during the radiation dominated period. And then yeah, how significant is the abundance is can be equal to total energy density of dark matter. So that's why it's called PBHDM. So an explanation of dark matter by primordial black holes. Yeah, and the dotted line is the future observational constraint, future observational sensitivity that is expected to further constrain power spectrum on small scale in the future. So yeah, let's go more on this violation of slow roll approximation. So, so the standard slow roll approximation means that we take we approximate this phi dot to be much smaller than this velocity. So we obtain this blue box. Yeah, slow roll approximation means this. So epsilon 1 can be written as the tilt of the potential, and epsilon 2 can be written like this, or both much smaller than 1. However, however, uh, let's say we have an extremely flat potential in the sense that this first derivative vanishing. In that case, then we have a condition called USR, or ultra slow roll. It means that the equation, I mean, the background equation of motion is given by this. So phi dot can be written like this, a to the power of -3. So as scale factor expand, the velocity of the scalar field decrease rapidly. So here epsilon 1 can be written as is proportional to a to the power of -6.
Yeah, again, so as space-time expand, then this become very, very small. Here, epsilon 2, given by this, is equal to -6, because phi double dot over phi dot h is -3 in this case. So you can see that the rate of change of epsilon 1 is very quick, is -6. Yeah, this violates Laurel approximation. Yeah, when epsilon 2, magnitude of epsilon 2 is order 1, at order 1. And this can be achieved simply by making the potential very, very flat, extremely flat, such as the first derivative vanish. So, yeah, typically we are interested in this kind of potential. So, yeah, we have to explain CMB observation on large scale. So here, at early time, the inflaton undergoes slow roll inflation, slow rolling down this potential, yeah, to realize slow roll inflation. However, at some point, let's say at TS, yeah, this inflaton undergo very flat potential until TE. It's called ultra slow roll here. But yeah, but inflation must be ended. So if yeah, in this part, fluctuation will grow, will be enhanced, but we have to terminate this enhancement to end the inflation. So we impose slow roll condition again here. And we can see that here there are two times transition. The first transition here from slow roll to ultra slow roll, and second transition is from ultra slow roll to slow roll. And then how to model this transition? So here I model the evolution of second slow roll parameter is like this. So at tau s, at the first time, first transition, uh, it undergoes sharp transition here, so instantaneous transition. However, after this first transition, uh, yeah, there are two model. The first model is a sharp transition again from this ultra slow roll to back to slow roll period, and then the second model is smooth transition, can transition like this. Yeah, so in this talk, yeah, I will explain the difference between these two models. So before that, yeah, I briefly review cosmological perturbation. So here we have perturbation in both the scalar field sector and the space-time and the gravity sector. So in the scalar field sector is simply given by delta phi, perturbation of this background phi bar. And then on the space-time sector is given by is embedded in this gamma ij and this lapse function and also this shift function ni, which can be solved by a Hamiltonian and momentum constraint after we define this gamma ij. But these are too general in the sense that we still have gauge degree of freedom. So we can perform gauge fixing condition. Yeah, there are many gauge condition, but here we are focusing on these two gauge condition. So first gauge condition is co-moving gauge. It means that the perturbation is represented by perturbation of space-time here, exponential to zeta. And the perturbation of scalar field is 0 in this gauge. And the second gauge condition is flat slicing gauge, where the perturbation is represented by perturbation of scalar field, delta phi. Here, it's like locally flat. Gamma ij is just the scale factor as function of time. And then there is a nonlinear transformation. So let's say we compute everything in flat slicing gauge. It means that we compute perturbation of delta phi. Here there is definition of zeta n. So zeta n is just a proxy of delta phi here. So we have this nonlinear gauge transformation, zeta equal to zeta n, which is delta phi, and delta phi square, and delta phi cube, and so on. Yeah, this is first introduced by Maldacena. So let's say we compute correlation function or mode function in this flat slicing gauge, then we can obtain correlation in comoving gates by this nonlinear gate transformation. Okay. Yeah. So let's see the linear perturbation theory or the second order action. Second order action in comoving gates, yeah, both comoving gates and flat flashing gates are only related by linear transformation. So we don't have to care much at this stage. It's given by this, and then if we define Mukhanov-Sasaki variable V, where Z is defined by this, the second order action can be canonically normalized to be like this. So this is like mass, like effective mass Z double prime over Z. And then equation of motion is given by this, where the effective mass can be expressed like this. So simply taking derivative of this Z in terms of epsilon1, epsilon2, and epsilon3. So this is exact formula of this effective mass. I do not perform any slow roll approximation here. And then let's say we perform slow roll approximation. It means that all epsilon1, epsilon2, epsilon3 are much smaller than 1. So we have Z double prime over Z, this 2 over tau square. Okay, so A is 1 over H. H is 1 over tau. Yeah, so we get this. However, interestingly, if we substitute condition for ultra slow roll, where epsilon1 and epsilon3 are very small, but epsilon2 gain order 1, we also get the same equation, the same Mukhanov-Sasaki variable, Mukhanov-Sasaki equation. Because yeah, let's just substitute this epsilon2 minus 6 and this epsilon2 square minus 6 square. And then we also get this 2 over tau square. Yeah, interestingly. But zeta are completely different because Z in ultra slow roll will be strongly time dependent. As we see here. So the general solution, let's say in ultra slow roll period, we get this. 1 over square root of epsilon. So here epsilon as function of time. In case of slow roll, epsilon1 is just almost a constant. However, in case of ultra slow roll, this epsilon1 strongly decrease. So 1 over square root of epsilon1 increase as function of a cube. And this is the mode function, which to be fixed by the initial condition. So let's say we consider pure ultra slow roll. Means that we have inflation with flat potential, completely flat potential. If we impose Banks-Davis vacuum, it means that we take only one frequency mode. Let's say we take positive frequency mode. So this is AK equal to 1 and BK equal to 0. So let's say we evaluate on the large scale, and then we get this, and we get spectrum like this, which a to the power of 6. So the spectrum is increase rapidly at large, evaluated at large scale. Here we already see super horizon evolution of scale invariant perturbation even at 3 level for this pure ultra slow roll model. Yeah, this is, so usually we get the constant mode in case of slow roll. Yeah, you can see that epsilon1 is a constant. But now, in case of pure ultra slow roll, we have evolution, a strong evolution for scale invariant perturbation, even at 3 level here. However, we see that in our case of interest, the ultra slow roll period deviates from Banks-Davis vacuum because the initial condition is not Banks-Davis vacuum. The initial condition is the end of slow roll period. So yeah, I go to this sharp transition. And then let's say we impose Banks-Davis initial vacuum. Here we get A1, A equal to 1, B equal to 0. And then we get the standard curvature perturbation, the standard mode function of curvature perturbation that we already know. Here epsilon1 is just almost a constant. Then during the ultra slow roll period, epsilon1 becomes strongly time dependent, strongly decrease. And so the curvature perturbation can be written like this. And then A and B are obtained by requiring continuity of zeta and zeta prime at the transition. So A is given by this, and B is given by this if we do the algebra. So yeah, let's define important wave number here. So Ks is defined as a wave number which crossed the horizon at the beginning of ultrasloral period. Ke is a wave number of mode function which crossed the horizon at the end of ultrasloral period. And we will see that the fluctuation will be enhanced within this range, Ks to Ke, later. So going to the second slow period, here, yeah, the curvature perturbation can be written like this. So again, epsilon is just a constant here, but already very small. So if we require continuity of zeta and zeta prime at this, the end of ultraslow period, yeah, do the algebra and we get this. Yeah, it's a mess, but if we plot the function, we get this. So this is large scale, almost scale invariant spectrum. Yeah, let's say, yeah, I label this delta S SR from the first slow period. Evaluated at K star here, let's say the CMB wave number corresponds to the CMB. Yeah, on small scale, here it enhance until delta S square PBH with ratio KE over KS to the power of 6. So this, yeah, this ratio. Yeah, it simply means the scaling of the slow roll parameter. So remember that slow roll parameter decrease a to the power of -6. And then it means that it increased a to the power of 1 over epsilon increase like a to the power of 6. And it corresponds to this ratio of this wave number, Ke over Ks. So yeah, we see that the fluctuation is enhanced, the power spectrum is enhanced between this Ks and Ke. And then at the end, I mean, at very, very small scale, it becomes flat simply because we impose slow roll condition, the second slow roll condition, second slow roll period after this ultra slow roll. Yeah, if we have another shape of potential like constant roll, then we can have like peak. But it means that we have to tune the period after ultra slow roll. Okay. Yeah, now we are dealing with large fluctuation. Does it mean that we have large nonlinearity? Yeah, so we have to be careful here whether linear perturbation theory is trustable enough. So let's say we have derivative of the potential. Yeah, here I define derivative of potential, like Vn is nth derivative of V. And then in flat slicing gauge, the leading cubic action is given by this. So V3 times delta phi cube. And remember that the shape of the potential is like inflection point. So yeah, within this inflection point, this V3 can be large. So in terms of slow roll parameter, it can be written like this, where zeta n is just linearly proportional to this delta phi. So if we want to compute, for example, like 3-point function, we can substitute this Hamiltonian of this cubic action, simply negative of this, to this in informalism, where the operator O is given by this. Then we define bispectrum after taking out the conservation of momentum, this. Yeah, after that, we can check the consistency of this bispectrum. So there is Maldaceno's theorem for this squeeze limit of this bispectrum. When we take one wave number to be very small, and yeah, we can, the result is given by this, where the coefficient here is the tilt of the spectrum. So now, let's say we compute bispectrum. The leading interaction can be written like this. Here, epsilon 2 prime. So yeah, remember that epsilon 2, we have sharp transition. So I mean that step function, and then epsilon 2 prime, derivative of the step function, is approximately Dirac delta function. So we can evaluate this f at the transition time, Te and Ts. So when we compute the bispectrum, we can compute this integral approximating this epsilon 2 prime as Dirac delta function. And if we do that, yeah, we get this bispectrum. And we can check, we can check the, I mean, at first we can think that, okay, it's strange. I mean, is it just like toy model of this Dirac function? I mean, whether it generate a consistent bispectrum, then yeah, we can mathematically check the squeeze limit. So the C naught from after performing that integral, we get C naught given by this C naught, this coefficient C naught K. And then when we plot, so we have the mode function, we have the exact formula, exact analytical formula of the mode function. When we plot, and then we get this, exactly overlap with the tilt of the spectrum. Yeah, so we can find that it's consistent. And then we can go further. So we can compute Bayer one loop correction with that interaction, going to second order in perturbation theory. So yeah, now the operator is 2-point function. And then the interaction is given by the same cubic interaction. And then if we compute that, we get this formula, one loop correction to general scale P. And then, yeah, if we approximate, if we are interested in a loop correction to the large scale or small wave number, small p, so the moment the loop has large on small scale, large momentum k, then we get this. We get this, and then if we substitute this, yeah, this is from the normalization of the Mukhanov-Sasaki variable simply by the commutation of the quantum commutation of the Mukhanov-Sasaki variable. We can show this. And then, yeah, if we compute the one loop correction to the spectrum, then we obtain this. Yeah, so it's like scale invariant one loop correction with the coefficient with the coupling constant is given by this 1/4 times delta epsilon 2 square. Yeah, yeah. If we naively evaluate this integral, for example, by cutoff regularization, then requiring this one loop correction to be smaller than this tree level, we obtain this condition. So yeah, it gives some light on what is the boundary of this theory. What is the limit of this theory when it become non-perturbative? I mean, naively from linear perturbation theory, we can just say that, oh, as long as the spectrum is still smaller than 1, let's say 0.1 and 0.001 10 to the power of -2, then we are still safe. I mean, we are still in the perturbation theory is still valid. However, here we have another scale associated with the transition of the second slow roll parameter. Here 1/, let's say 6 square. Here we have another scale that we have to take care, I mean, whether we are in the valid domain of perturbation theory. Yeah, and then, yeah, we can compute the trispectrum. Yeah, this is still work in progress. So trispectrum contain an exchange diagram and contact diagram. Exchange is summing S and T and U channel given by this, computing by this, and contact diagram, you computing this from the, yeah, so the contact diagram is obtained by this quartic action from the fourth derivative of the potential. And then the quartic Hamiltonian is given by this in terms of slow roll parameters. And then, yeah, the explicit form of the trispectrum is too long, but we can show that it satisfies Maldaceno's theorem. So it means that squeeze limit satisfies the running of the bispectrum. So squeeze limit of trispectrum is running of the bispectrum. And then also collapse limit of this trispectrum, we can see like factorization of this bispectrum. Okay, this is also work in preparation. Yeah, here we can evaluate the soft limit of the trispectrum and the running of bispectrum. So it's perfectly matched. And then, yeah, we can compute Bayer one loop correction after including this contact diagram. So the contact diagram will give this diagram. And to general scale P is given by this. Yeah, and then if we approximate for, let's say we are interested on large scale, so small p and then large loop momentum. Yeah, summing the contribution from cubic Hamiltonian, we get this. And then, yeah, if we use like naive cutoff regularization, let's say we put cutoff from Ks until Ke, we get this formula for the one loop correction. Yeah. So physical picture of this bare one loop correction is like at the transition, this small scale perturbation coherently kick this large scale perturbation. Yeah. So yeah, this kick is given by the loop correction. Yeah, and it's scale invariant loop correction. So yeah. So previously I discussed this sharp transition at both at both here and here. And we see that all the contribution of the loop correction comes from the second transition, where the fluctuation is already large, and then this large fluctuation enter to the loop. Yeah, so it make the loop large, and then yeah, so yeah, this looks dangerous. And then the question is, can we make the transition smooth, such as we can have small one loop correction or small nonlinearity? Yeah. So here at first, in some previous slides, I already give introduction on this. I mean, like puzzle. So it's at first it looks that the Mukhanov-Sasaki equation for the slow roll and ultra slow roll are the same, right? So z double prime over z is given by this 2 over tau square. So the effective mass divided by Hubble is simply given by 2, m square over 8 square. Yeah, so this is in the regime that if we only consider almost constant epsilon 2, means that epsilon 3 is very small. So this same Mukhanov-Sasaki equation, but different physical condition is called Wand's duality. So it's related slow roll and ultra slow roll. They have same Mukhanov-Sasaki equation. However, now how if we have dynamical epsilon 2? Let's say epsilon 3 can be order 1. Turns out that we have another physical situation that also leads to z double prime over z given by this. Now that if we have this condition, this plus this, 3 over 2 epsilon 2, 1 over 4 epsilon 2 square, and this half epsilon 2 epsilon 3, this. If this equal to 0, then we also have this z double prime over z is approximately 2 over tau square. Yeah, turns out that we have this another condition of the transition that can realize this effective mass. So it's called Wand's duality. Yeah, so now how if we have smooth evolution? So let's say this is the horizontal axis is time after the first transition. So yeah, so at first it's -6 is here, ultra slow roll period, and its transition until the slow roll period again 0. Yeah, so now let's say let's take that that previous equation, this Wand's duality condition, and let's say it's equal to 3 over 2 delta, where delta is a very small, almost 0. And this is the for various delta, 0.01, 0.005, 0.001. And then here, if we this right picture, right panel, if we plot eta prime, the derivative of second slow roll parameter. Yeah, sorry, this should be epsilon 2 and epsilon 2 prime. Yeah, if we plot this, the derivative of second slow roll parameter. And then, we get this. So the second slow roll parameter is almost constant here and also almost a constant, and it's peak in the middle, this transition. Okay. So, if we have that smooth transition, smooth second transition, we can evaluate the curvature perturbation like this. And then if we plot, it will be given by this. So this is for various delta. Yeah, if we compare the smooth and sharp, so for sharp transition, so if we have sharp second transition, then we have small artifact here, like small decrease here, until it's stabilized again to the very small scale. However, if we have smooth transition that satisfy one's duality, yeah, so here I specify the smooth transition that defined by this transition, defined by this. Then we will have this spectrum on small scale. So yeah, almost a constant here. Yeah. So turn out that this is interesting. Interesting condition. Interesting. Yeah, we will have interesting feature here. So yeah, take again the differential equation of this one's duality given by this. And then if we take time derivative, we obtain this equation. And then we can show that epsilon 1 times a squared times epsilon 2 prime is a constant. So yeah, if we evaluate this derivative, and it will be 0. So therefore, back to the interaction, turn out that the interaction can be completely 0. If we evaluate this quantity, a squared epsilon 1 epsilon 2 prime. So if we impose this one's duality condition, turn out that it's a special smooth transition that relies no nonlinearity. So zero nonlinearity. And then we can also get this quartic coupling also 0. And then so the bigger picture of this of this talk is that deviation from one's duality condition generate higher order correction to the correlation function. So here I make a plot of effective mass. Effective mass is z double prime over z, but multiply by this AH minus 2. So yeah, the first scenario is sharp transition both at initial and the second transition is given by this gray curve. So it's like Dirac delta function of this z double prime over z at first. And then second time also it's Dirac delta function of z double prime over z.
Hi, we have 4 minutes left.
Okay, good. And then, yeah, if we have smooth second transition, turn out that we can have a curve like this. So this is a constant. Z double prime over z is 2, almost 2, yeah, given by this. And then this make nonlinearity almost vanishes in this smooth transition scenario. And this confirmed by non-perturbative lattice simulation in this very recent paper. And then, yeah, this give a guidance maybe for Bootstrap because like recently cosmological Bootstrap is developed. For example, like we have slow roll inflation, and then slow roll inflation can be approximated from small breaking of de Sitter space. And then here, perhaps it can be a possible guidance that deviation from one's duality condition here give induce large nonlinearity in the case of inflation model that strongly violates slow roll approximation. Okay. Then we can ask about how to renormalize this diagram. So we already discussed cubic and quartic interaction, simply cubic derivative and quartic derivative of the potential. And then this is all the diagram. So previously I present the 1pi diagram, the 1pi of cubic, 1pi of quartic. But there are another non-1pi diagram. So this is non-1pi diagram to the 2-point function. To the 2-point function like this. And then this is the zero mode here. And this is the loop. And also there is contribution to the background, to the 1-point function is given by, this is schematically given by this diagram. This is zero mode also. Okay. And this is recently is discussed. So at first there is this paper on renormalization of this linear counter term. And after that is discussed by Inomata and Brackley and Pinol, and we also make a claim about this. So, yeah, this cubic coupling, previous cubic coupling, induce a loop correction to the background is given by this. And then we can, yeah, we can renormalize this. We have to renormalize this by this linear counter term, this, let's say, delta V1, and then imposing the this renormalization condition. So if we impose this renormalization condition, then we fix the counter term. We completely fix this delta V1 is given by this, where this delta phi square is defined by this. Okay, this loop. However, yeah, this is what is interesting. So this linear counter term non-linearly induced quadratic counter term. Because if we have first derivative of the potential, then we can compute second derivative of the potential by this. So delta V2 is delta V1 dot over phi bar, over the background, the phi bar dot. And then, yeah, delta V2 is given by this. So yeah, at first this quadratic induced counter term is discussed in this paper by Pimentel, by G. Pimentel et al. And then, yeah, also discussed by Inomata and Brackley-Pinol, and also, yeah, we make claim about this. So, turn out that this V4 delta phi square here has same structure with this loop, yeah. So, turn out that this diagram and this diagram is cancelled. And then this diagram, the right panel. So if we have previous renormalization condition on the zero mode renormalization condition or tadpole renormalization condition, like this plus this is 0, then this diagram also canceled. So we are left with this diagram. And then what happened with this diagram? So yeah, we cannot proceed more because, yeah, without regularization scheme, mathematically this is infinity plus minus infinity. And then to proceed, we must specify a regularization scheme for both the second order perturbation theory and then first order perturbation theory. Yeah, and then as we know from mathematics, like if we have limit of infinity minus infinity, we have to specify what is the we have to specify what is the infinity. Otherwise, it's undetermined in mathematics. So, yeah, mathematically, it leads to it yields a finite term that depends on scheme, that depends on how we define the infinity. Yeah. However, this counter term is just induced from the linear counter term. So because it's induced, then it's completely fixed by the renormalization condition of the one-point function. Thus, we cannot absorb the ambiguity of the finite term to the quadratic counter term. Because, yeah, we are familiar with quantum field theory in Minkowski space on in flat particle physics. Then usually this ambiguity of finite term can be absorbed to the finite part of the counter term. However, here, yeah, we have to remember that our counter term is already completely fixed by the renormalization condition of the one-point function. So we don't have any any part to absorb this ambiguity. Thus, we need counter term beyond background renormalization. And then, yeah, this is my conclusion. So here, present cosmology for inflation model with large fluctuation has just begun. We have presented cubic quartic coupling that yield consistent correlation function at second order perturbation theory, bispectrum, trispectrum, and bare one loop correction. We have identified coupling constant associated with the transition of second slow roll parameter. Also, we discussed the importance of one's duality. Yeah, this importance to go further. So after we understand constant interaction, we can proceed to compute one loop power spectrum at small scale to make prediction of whole spectrum. And then whether we can renormalize the whole spectrum. That's the next goal. So thank you. Thank you very much.
Okay, so thank you for the nice talk and a nice presentation. Any question from the audience, please unmute yourself and ask. Okay, I have one question. So you only talked about
Uh-huh.
the
Hmm?
scalar sparse spectrum and the loop correction in the scalar sparse spectrum, right? And higher order functions also.
Yes.
So
Hmm.
have you also considered the possibility of the tensor sectors? So at some point of time, the tensors and scalars get mixed, right? So
Yeah,
what
yeah.
kind?
So recently also there are some claim about that, especially by, if I remember, the Hong Kong group, right? The uh, Wang Yi and Atsui Saota. So recently there are also some claim about loop and this Chinese group also in, yeah. So recently there are some claim about this loop of the uh tensor power spectrum, but the loop is excited scalar. Yeah, yeah. Some people already try to compute it, but still, yeah. Yeah, yeah, exactly what you say. So some people
Uh,
already
and
computed.
yeah, and then what is the claim that these also get large or something, or they can be controlled? Or
So some claims say it there is evolution also. I mean, it can be large. I mean, evolution outside the horizon of this tensor power spectrum. But some other claim also counter argue this that uh, yeah, that after performing more careful calculation, it can be cancelled somehow. Yeah, yeah. I'm not sure whether cancellation is also like renormalization condition here, like imposing this renormalization condition, or yeah, cancellation like this. But yeah, still, yeah, I have to study on that claim.
okay, okay, thank you.
Yeah,
Any
yeah.
other question from the audience? Okay, it seems not. So let's thank the speaker one more time. Thank you for the nice talk. Will you be able to send us the slides for our seminar library?
Yes, yes, I can. Yeah, I can share.
Okay, thank you.
Share.
Thank you. So let's move on to the next speaker. Yes, do you hear me?
Yes.
Okay, okay.
Do you
Thank
hear
you.
me?
Yes, yes. So I need to ask your permission to make your talk live on our YouTube channel because some people join via YouTube.
Yes, that's fine.
Okay, so just give me a moment to start the YouTube.